that oscillates
Yeah.
a lot towards the center.
Right, because for very small changes in x if x is close to 0 and x changes just a little bit, 1 over x changes a lot, right? Because the graph of 1 over x is very steep near 0. So what happens is the graph comes in here kind of gentle, but then it gets like this. And of course it doesn't actually have a value at 0, and of course this should be there, that should be there. Okay, so that's basically how it would look. So it looks like it's oscillating wildly as x gets close to 0. And of course we're never plugging in 0 for x, so that doesn't matter to us. But x's that are close to 0, we have this function kind of oscillating wildly, and it's being multiplied by something that's, about 3. It's about 3. So based on that, what do you think? Do you think this limit exists? So take this wild graph and amplify it by a factor of 3. So now your humps are going up here like this between plus and minus 3, more or less.
Is sharing.
Doesn't seem like it, right? The function is not settling down on a value. You have to have both. The thing with Math 350, you have to have both the intuition and then the rigorous proof to follow it up. But the intuition should be that this does not exist. And that's going to turn out to be the right answer. Now, if we think that the limit does not exist,
Contradiction.
how do we prove that the limit of a function does not exist?
Using sequences?
Correct. Using the proposition 4.6. Exactly. Very good. So actually, let me come back over here and let's try and use that. Okay, so what we need, if you remember, so we use proposition 4.6. Okay, remember that, what does that say again? It just says that the limit of f of x as x approaches c is equal to L if and only if anytime xn converges to c and xn does not equal c, then, so if this is true, then f of xn converges to L. Okay? Does that make sense? Okay, so what we need is a sequence that converges to 0. And we want to make it a sequence that we can plug in the terms into this function. So I've got this thing covered up too much. Okay, so that's the thing that we're looking at. So does anybody have a suggestion for how to make a sequence that converges to 0?
Can we use 1 over x?
1 over n.
1 over n. Let's try 1 over n, where n is a natural number. Okay. So obviously that does go to 0 and doesn't equal 0. Okay, good. So then let's look at f of that. So f of xn as a sequence would be, well, 1 over n plus 3 times sine of n, right? And does that converge to something?
No.
No, it doesn't. This doesn't converge. Does anybody know how to prove that?
Because there is a thing that says if a sequence converges to a specific limit, then every subsequence must converge to the same limit. And
So by way of contradiction, suppose that this does converge. Let's say it converges to L or something like that, right? You could think about using subsequences, but we don't actually need to.
We know sine
sine
doesn't converge, right?
Right, this one does not converge. So what I'm going to propose that we do is I'm going to propose that we write sine of n as 1 over n plus 3 times sine of n over 1 over n plus 3. This is the clever way to do it, right? The numerator converges to L by assumption, And the denominator clearly converges to 3, right? This converges to 3. Okay, so we're saying that the sign, so this is by limit laws. By limit laws, and that contradicts, so that contradicts the fact that sine of n does not converge. Okay, contradicting the fact that sine of n doesn't converge. Why doesn't sine of n converge?
Because it has two different subsequences that converge to
But what are you going to write on your paper if it's a question?
maybe a homework problem.
Good, by the homework. That's right. So we can always go back and give all the details, but if you've seen it before and you've done it before, you can just quote something that we've seen or done in the past. Okay, great. So that's the reason. Sine of n doesn't converge, but here we seem to have shown that it did converge. Okay, great. So now we're done by proposition 4.6. We found a sequence that converged to 0. The image of the sequence did not converge to any number at all, so there is no L here on this problem. There is no limit to this function. Make sense? Kind of nice. Nice and good. You don't want to try and disprove limits by using epsilons and deltas. It's just way too difficult. This is a much, much better approach. Okay.
Is it possible to do that?
Yeah, I'm not going to say it's impossible, but of course, when you try to set sine of 1 over x times the quantity x plus 3 less than epsilon, and try to solve for x, it's going to be difficult to come up with a delta that really does the trick for you. So it's cleaner to do it this way. Okay. Everybody so far so good?
Yeah.
So far so good. Okay, I just have one more. This last one's a little bit of a different type of a problem, but I like it a lot, so it's good to go over it here. Let's suppose that f goes from the closed interval AB to the real numbers r is increasing. Now, increasing just means that, i.e., if x is less than y, then f of x is less than or equal to f of y. Let's just assume that that's the case. And then what we're going to prove here, f is continuous at a if and only if the infimum, oh boy, some old ideas coming back, the infimum of the f of x values where x is an element of the half open interval, so open at a and closed at b, the infimum of that set is equal to f of a. This is what we are going to prove. Okay. That is what we want to prove. I think I'm going to start off by reminding you what f continuous at a means. Okay, so f is continuous at a means, okay, for all epsilon greater than 0, there exists a delta greater than 0 such that if x is in the domain of the function, in this case that would be the closed interval a, b. Well, let me just write it as d for now. If x is in D and absolute x minus c is less than delta, then absolute f of x minus f of c is less than epsilon. So we just started on this on Wednesday, so I'm already hitting you with a problem on it. In this case, you do allow x to equal c. There's nothing that requires that to be different, and the L is just f of c in our usual limit definition. So these are the definitions here. Okay, everybody with me? Now let me just it might help to actually just draw an example here. So suppose we have the interval from a to b, right? And this is an increasing function, so it means it has to go up, up, up. It can be flat, but it more or less has to go up. And what we're doing is we're looking at the infimum of all of the output values of this function. So that would be, everything that's on the y direction, basically from here to here, right? These y values. And the idea is, and of course we're using the open interval here and the closed interval here, the infimum of that should just be whatever f of a is. This value right here. That's what the picture is kind of showing. Does that make some sense? Okay. So that's the idea. Of course, if f was not continuous, let's say it was not continuous at A, then intuitively that would mean that the graph isn't there, it could be plotted down here, right? Well, now the infimum of this set is still here, but the f of A value would be way down here. That if the function was not continuous at A, this would be the problem. F of A is way down here at this y value, but the infimum of this set of outputs on this interval would still be where this open dot is. That would be two different numbers which would not agree. So this would not be equal in that case. Does that make sense? Kind of got the intuition behind it. So this picture kind of helps you to see what has to be going on. Continuous just kind of means, you can draw the graph without picking up your pencil. So if I have an open circle and then I plot the point somewhere else, well, then you're picking up your pencil to do it. So that would not be continuous. But the way it is now, the way I filled it back in, yeah, I can draw this whole thing with one continuous motion. I never have to pick up my pencil. Okay. Well, we have to prove this both directions. So forward and backwards. So I'm going to start with forward. Okay. So I'm going to assume f is continuous at A. And I'm going to try to show that my infimum of this set is just f of A. Let's remember what infimum means. It means f of A has to be a lower bound for the set and then a greatest lower bound for that set. So we're going to check both of those things. So I'm going to claim f of A is a lower bound for this set f of x such that x is in the half open interval from A to B. Okay? Can anybody tell me why that's true? This is a quick one. Why is f of A a lower bound for that set?
Since f is increasing, A has to be this. Since f is increasing, that means that if A is less than any point on.
Notice x is bigger than A, right?
Mm-hmm.
Okay, so if A is less than x, that implies what now?
F of A is less than or equal to f of A.
There we go. Perfect. So f of A is less than or equal to everything in this set. Okay? Perfect. Great. That's it. That proves that f of A is a lower bound for that set. Okay, now what I need to do next is I need to claim if gamma is a lower bound. By the way, that first part did not even use the assumption. We didn't even use the fact that f is continuous at A yet. So if gamma is a lower bound for the set of f of x such that x is in the half open interval from A to B, then we want to prove that gamma is less than or equal to f of A. Okay, so this part will take a little more work. So this is the two parts of proving that the infimum of a set equals a certain number. You show that it's a lower bound, and then if there's another lower bound gamma, it should be less than or equal to any lower bound that you might have started with. Okay. So gamma is less than or equal to all of these values. So in terms of the picture over here, gamma, so this is f of A and this is f of B. Gamma is going to be somewhere down here, right? Smaller than f of A. That's what we're trying to prove. Any suggestions how we might do that? And remember, we're going to need to use the fact that f is continuous at A. Because f is continuous at A, for all epsilons greater than 0, there will exist a delta such that blah, blah, blah. Can we see where we're going to get, I mean, how are we going to get an epsilon that's greater than 0 that we can actually sink our teeth into? This is not one of those proofs where you write, let epsilon greater than 0 be given. That's not what we're going to write, because we are assuming already that continuity is true. We're assuming f is continuous. So that means we can already be assured that given any number epsilon greater than 0, the rest of this follows. How am I going to get an epsilon that's greater than 0 to which I can apply that?
We go gamma minus f of A. Or
Okay.
minus gamma.
Well, this is what we want to prove, right? So to make a positive number out of this, what I can do is go by way of contradiction. Right? So by way of contradiction, suppose gamma is greater than f of A. Suppose gamma is greater than f. So in other words, suppose that gamma is maybe right here somewhere. Right? Gamma is above f of A. So now, how can I make an epsilon that's greater than 0? Say again?
Gamma minus f of A.
Exactly. Gamma minus f of A. Gamma minus f of A, that's greater than 0. Perfect. Okay, so we have that. Gamma minus f of A, that's epsilon. Okay, so for that epsilon, there already exists a delta. Okay, so since f is continuous, sometimes I abbreviate continuous CTS. Since f is continuous, there exists a delta greater than 0 such that if x is in the closed interval AB and absolute x minus A is less than delta, then absolute f of x minus f of A is less than epsilon. And we're going to hopefully get a contradiction out of this. Make sense so far? So we made an epsilon that was greater than 0. That produces for us a delta such that as long as x is in this interval, by the way, we won't even need these absolute value bars here because x is going to be at least A anyway. So this is really just x minus A less than delta. Then f of x minus f of A is less than epsilon. Okay.
If you put in gamma minus f of A for epsilon, and you're saying that f of x is greater than f of A, you can drop the absolute value bars,
Right. Yeah, we're going to be able to drop all those absolute value bars. Exactly.
and then you can add f of A to both sides and get f of x less than gamma. That's a
Right.
contradiction.
Right, exactly. So, okay, good. So let's choose an x in the closed interval AB with x minus A less than delta. Okay? Then f of x minus f of A is less than epsilon. And I don't need absolute value bars on that, on any of those, because x is bigger than A already. And f of x is bigger than f of A because of the increasing, the function is increasing, right? Okay, good. So f of x, actually, you know what, let's do this. Can I come back here for a second? Let's just really make this clear. Let's just choose it as x naught, just to make it really specific. So there's an x naught, f of x naught right here. So f of x naught is less than f of A plus epsilon, and f of A plus epsilon is just gamma. That is just gamma. And now what do you have? You have gamma larger than some value f of x naught. But gamma was assumed to be a lower bound for that set. Gamma was supposed to be less than or equal to all f of x's. And here I have an f of x, namely f of x naught, that gamma is not less than or equal to. So this contradicts gamma being a lower bound for the set of f of x such that x is in the half open interval AB. This, right, exactly. Okay. Does that make sense, guys? Make sense? Okay, perfect. Let me just make sure that I am happy with that. Yeah. Yeah, that looks good. Everybody good with that? Okay, let's do the proof the backwards way. Let's go back the other way. Erase this part here. Those of you watching at home can rewind this if you need to look at it again. Now we're just going to, this is the last thing for today, we're just going to try and prove this way around. Okay. I'm going to assume that the infimum of f of x is equal to f of a, and I'm going to try to prove that f is continuous at a. So to prove that f is continuous at a, here's my definition over here. So I'm going to start off now with this direction. Yeah, we start off with let epsilon greater than 0 be given. And our job is to come up with a delta. Okay. So the greatest lower bound of the set of f of x's is this. So anything that's bigger than f of a is not a lower bound for this set. Is there a way of making something that would be bigger than f of a